The objective of this video is to establish the relationship between winding factors and the current linkage of a phase winding, and then winding factors and the electric loading of a three-phase machine. So we've previously developed winding factors based on the star of slots as telling us the harmonic content in our back EMF. In this video, we're going to show how they relate to the current linkage that's created by a phase winding. And then we're going to show how they can be used to determine the electric loading of a three-phase winding. And the last point of this is extremely important from a design perspective. We're going to derive an expression for our electric loading that depends on the number of ampere turns in our slots and our winding factor. And so this will become a fundamental design equation for the class. You'll be able to use this to figure out how many ampere turns you need in a slot given the winding layout that you've designed. But let's start at the beginning with deriving the expression between the relation between winding factor and current linkage. And to do that, let's review a few things. So given this coil that I've sketched on the left, which has an arbitrary coil pitch of gamma and is located at the specific angles of alpha 2 and alpha 1, we can calculate the pitch factor as being the sine of our harmonic index V times the number of pole pairs times gamma divided by 2, and then with this angle that I've given up above. And we have also, in a previous video, determined what the current linkage of this is in a Fourier series representation in the phasor form, as shown here. And then finally, we've talked about the relation between N and V. So N is the harmonic index given one revolution around our stator, going from 0 to 2 pi radians, mechanical radians around our stator, while V is the harmonic index of our number of pole pairs. And so one of these expressions, the pitch factor, we've written in terms of V, while the current linkage we've written in terms of N. So we're looking for a relation between the current linkage and the pitch factor. So we'll start by rewriting the current linkage in terms of V and reshuffling a few terms here. And so I've come up with this expression, and looking at this expression, we can note that these terms right here correspond to our pitch factor rotated by pi by 2. So you can easily see that by looking at this expression up here, and if you were to rotate it counterclockwise by pi by 2, it would clearly be this expression. And so we're going to make that change and then reorganize a few more terms. And at this point, we're going to define this phasor, which we're going to call we're going to denote it as our current linkage of some fictitious coil 0 and a certain harmonic V. And we're doing this for notational convenience. It's going to make our expression a little bit simpler. This entire expression to here is going to be the phasor of our current linkage of coil I. So you see that in all these equations, I am denoting this coil as being coil I. That's why there's a subscript I in our current linkage, our winding factor, and our phasors. And next, we'll note that for a complete phase winding, we have several coils that are connected together in series. We can get this expression, which is that the phasor for our complete phase winding is equal to this theta bar prime that we defined, this phasor for coil 0, times the summation of our pitch factors. And I want you to recall one more thing in order for us to take the next step. Recall the definition of our winding factor. Our winding factor, we calculated it as this summation. And we can note that that looks awfully familiar or awfully similar to what we currently have right here. In fact, this quantity is equal to N times our winding factor. And again, the winding factor is a complex quantity, which is why we've denoted it with a phasor. So it has a peak value or a magnitude. It has a magnitude and a phase angle. So we can now write an expression for our current linkage phasor in terms of our winding factor. And if we pull this all together, we can come up with an expression for our current linkage. We can take the real part of this times e to the j vp alpha. So we're evaluating this full expression up here in terms of our winding factor magnitude and angle. And so we end up with this expression. And this is a pretty important expression. It shows us that we can calculate our winding factors from our star of slots diagram, and we can use the winding factors that we've calculated to construct an expression for each harmonic of our current linkage. This is a harmonic of the current linkage of the complete phase winding, so it's when we've added all of our coils together in series. And this is a nice fundamental result that shows us that the winding factor truly is a primary variable, a fundamental aspect of our electric machine. So when we lay out our winding, suddenly we know both what our back EMF will look like, and we also know what our current linkage and our air gap will look like. So going back to our objective up here, we've now completed objective number 1. We've related our winding factor to the current linkage of our phase winding. Next, we're going to move on to relating the electric loading of our sizing equation to the winding factor for a 3-phase winding. And when we do this derivation, we're only looking at the harmonic of v equals 1. That's because that is the harmonic that we've maximized when we laid out our winding. We're trying to create only fields of that harmonic. We want purely sinusoidal fields so that we don't have torque ripple or extra losses. And that is the primary harmonic that contributes to our torque creation, so that's the harmonic that we derived our sizing equations for. So again, we'll focus on harmonic v equals 1, and if we write out an expression for our current linkage of our phase U winding, it's going to look like this. And you can see that I'm showing the magnitude of our winding factor. I'm not showing the angle of the winding factor because I'm assuming that I have located this winding so that the MMF peaks at alpha equals 0. I'm assuming that the winding factor for harmonic 1 is 0 of the phase U winding. And I can rewrite this in terms of the current in my conductors in the slot. That is plugging in a value of theta pi of ZQI by 2. And I've got a terminal current of IU, phase U terminal current. So we've talked about how we can go between having a current linkage and an equivalent circumferential current density that creates that current linkage. And so I'll write that down now. And so this is the expression that we used when we derived our sizing laws. When we talked about the equivalent rotating circumferential current density, we assumed that each phase winding had an equivalent circumferential current density of magnitude ACPH prime, and we had the prime there because it was normalized by the current. So if we multiplied that magnitude by our current, then we had that multiplied by a sine, and that was what we modeled when we derived our electric loading. So I've written this out just for one phase winding, but we would do the same thing for phases V and W, just shifted by 2 pi by 3. So for example, phase V would look like this. Excuse me, before I write that, I want to note one more thing here. So we came up with this expression down here, and we can note that this quantity right here, this quantity is equal to this ACPH prime divided by the number of poles of our winding. That was a result that we derived when we established this equivalent circumferential current density, that the magnitude of the current linkage was the magnitude of our circumferential current density divided by the number of poles. This is a result from a previous lecture that I'm summarizing here. So to save space, I'm going to write the magnitude of our phase V current linkage using that result. And then we can write the same type of expression for phase W. We have these current linkages for phases U, V, and W, and the fundamental is phase shifted from each other by 2 pi by 3. That is the phase angle of a 3-phase system. We we always shift our current linkage and our voltages by 2 pi by 3 between phases. So we've got this expression for the current linkage, this expression for the circumferential current density for phase U, and as we derived in our video, we would have the same thing for phases V and W, just shifted by 2 pi by 3. And so we then combine this with 3-phase currents that were also shifted by 2 pi by 3. So we had these expressions for circumferential current density, and we added to that 3-phase currents of a magnitude I hat and an angle of alpha W. And that is what we use to drive our electric loading. So let me summarize where we are. At this point, everything that I've just put on the screen is a review, except this quantity right here, which we've derived in the video lectures for today's lecture. But all the rest of this, all these expressions here, all of this is all a review from our machine sizing unit. So when we had these results, we showed that we could drive our electric loading. And our electric loading was our linear current density when we have all 3 phases excited. And we had an expression like this, where A hat is the electric loading, and that was limited by the cooling conditions of our machine. So if it was an air-cooled machine, we had something like 30 to 80 kiloamperes per meter, and if it was liquid-cooled, we could go much higher. And we related that back to this quantity ACPH prime using the radius and this factor 3/2. So what we're going to do now is we're going to take this expression right here, and we're going to plug in this quantity into it to get an expression for our electric loading in terms of our winding factor and the slot current in our slot. And when we do that, we get the following. We get this expression, which is one of the more important expressions that we'll drive in the class. This, again, relates our electric loading, so that fundamental property of the machine, the number of kiloamperes per meter that we can produce, which is limited by our cooling, we are relating that to our winding factor and geometric dimensions of our machine. It's got our air gap radius, it's got the number of conductors that we have in a slot, the current, the rated current that flows in those conductors, and the number of coils that are connected in series for a phase. And so this is a design equation. We typically will know what we desire for A hat for our electric loading, because we know how we're going to cool the machine. And the value N is related to the number of slots. So this is the number of coils that we have in a phase in series. And so if this is a 2-layer winding, it's going to be equal to our number of slots divided by our number of phases. This shouldn't come as a surprise to you. If it does, just take a moment and think about how you would determine how many coils you have in a phase winding based on the number of slots and the number of phases. And if you have a 1-layer winding, a single-layer winding, it's going to be Q divided by 2 times the number of phases. R is our air gap radius, and KW1 is our fundamental winding factor. And remember that KW, our winding factor, is always less than or equal to 1. And in order to use our slot current the most effectively, we want to have KW be as large as possible. So we'd like to have KW1 equal 1 if it is possible, because that means that we require the fewest number of ampere turns in order to realize this linear current density. So we'll take this expression and then we will solve it for our ampere turns that we require in the slot. And that is a fundamental step in our design, our analytic design of a machine. So if we think a little bit about what we've done in this video, we've related winding factors to our current linkage. So we've said that if we lay out a winding and we calculate our winding factors, we can determine an expression, an analytic expression for each harmonic of our current linkage of our complete phase winding. So that's an important result. And then second, we've noticed that the fundamental component of our current linkage can be treated as an equivalent sinusoidal circumferential current density. And so that opens up the toolbox that we developed when we were in the motor sizing unit, when we considered motors as only having windings that consisted of sinusoidal current densities. So now we're saying that our fundamental harmonic is like it can be modeled as a sinusoidal current density. And if we use that, we can derive an expression that relates our electric loading to the required number of ampere turns that we need in our slot based on the winding factor. And this points out further the importance of the winding factor. It tells us how effectively we're using our ampere turns to create torque in our motor. If we have a very low winding factor, if kW1 is like 0.1 or 0.5, that means that we require a very large value of ZQI in order to create the same electric loading as if kW1 was very large. So in conclusion, the winding factor is very important. This expression right here, knowing how we got it and what it's used for, is extremely important for the class. So please take some time and reflect upon this video and these notes, and we'll see you in class.